welcome back. It's time for our second video in the series here about acceleration. So this particular one, we're going to be looking at creating velocity time graphs. This is just an introduction to what VT graphs look like and some of the characteristics of them. There will be a later graph in the series, later video in the series, where we look a little bit more in depth into interpreting different shapes and types of VT graphs. So again, this was just an introduction of some of the items when we set them up and how to do some basic interpretation of them. So we'll take a look at briefly what motion diagrams are. How do we graph it if something's velocity is changing versus staying the same? And then how do we look at the ideas of acceleration on graphs, instantaneous and average acceleration? Just going to briefly touch on that topic. So moving on here, what do we got? So if we're going to do a velocity time graph, we need to be thinking about how something is moving. And we've been using these particle models or motion diagrams, however you want to call it, to represent some different types of movement that's on here. So remember, if we're talking about what's happening when an object is going constant velocity, right? It's covering the same amount of displacement in each time interval. That's constant speed or constant velocity. But if something's accelerating, you can kind of see in our little Guido diagrams over here on the top, that if it's accelerating, right, the amount of displacement that it's covering per interval is getting bigger. Or if it's accelerating even faster, right? It's not just growing like that, right? It's getting bigger, right? A lot faster. So we can start to talk about the different rates of changing in speed. And that's what we're trying to quantify with acceleration. We can also talk about the difference between speeding up and slowing down, right? These are both considered to be forms of acceleration that we can represent in motion diagrams and in VT graphs. I'll remind you that there is a third way to accelerate, right? So increasing your speed, getting faster, decreasing your speed, getting slower are two commonly understood types of acceleration. But because velocity is a vector and acceleration is a vector, you can also be changing direction. And any time that something is turning a corner, going in a circular motion, it's constant acceleration actually, or it could be changing acceleration too. So depending on what it is, if it's changing directions, that's also considered to be acceleration. So speeding up, slowing down, and changing direction are also considered to be acceleration points. In our particular chapter that we're doing right now, we're dealing with linear motion. So we're really only going to be doing the speeding up and slowing down. If we get to rotational motion, that's where we start to talk about changing direction. So it's a little bit of a different type of thing we'll talk about later on in the year. So what does this look like if we're going to try to draw a graph of something that's changing its motion over time? So we'll start with an easier one. Constant positive velocity, like our cyclist here. Let's say he's just coasting. What's actually happening in terms of his speed if he's got velocity over time? Again, now take a look at what I've set up here. I've got velocity is on my y-axis. I've got time on my x-axis, so that's important. And then notice how I have a positive and a negative section for my velocity. I'm going to try to do graphs more like this to keep us from thinking about going forwards and backwards. Think of it as going east and west or north and south. Much better way to think about what the positive and negative side means on here. So maybe we can say that in this particular case, if we want to define it, let me get my pen going here. Maybe we're going to say that this particular direction is east. That was a weird E. And this direction over here is west. So east is that way, east is that way, I guess. Anyway, the way the cyclist is facing, west is the other way. Again, positive and negative velocity. So if he's going forward, like this cyclist looks like he's heading east here, maybe he's going at 10 meters per second. Well, what's he doing over time? He's doing 10 meters per second, then he's doing 10 meters per second, then he's doing 10 meters per second, then he's doing 10 meters per second. And all that would look like on a graph like this, a VT graph, is something along those lines. If I can draw this actually relatively straight. Like that, right? He's going 10 meters per second, 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 right? He's still moving. Remember, his DT graph, if we did this, would be going like this. He's going 10 meters per second, but he's going at an interval all the time, right? He's covering distance each time. His displacement from start is increasing each interval, but his velocity is staying the same. We see this regularly, where a DT graph has a nice straight line at an angle, and then the VT graph may be a horizontal line. So again, that's a very common, consistent pattern. So the VT graph, constant velocity over time. What's the slope here? Right? If it's constant velocity, the slope of a VT graph is 0, constant and positive. Okay, constant negative velocity. So here we have our little friend here moving to the west. He's going this direction, right? He's going that way. Maybe he's coasting. Now, he's not going as fast because he's a little dude, right? So if we're going to draw him, maybe he's only going 2 meters per second. But if he's going constant negative velocity, we can't draw our line here because that line indicates 2 meters per second east. So be careful with your directions here because he's going to the left on the screen. That means he's going 2 meters per second this way. His actual velocity is this way, negative 2 meters per second, which also would mean west. That's what that means in this particular case. East to the right, west is to the left. Now, you wouldn't necessarily draw like this way if he's going to the east or something like that. That's not what that means. The positive and negative sign is what tells you the direction of motion. So if he's going on that left side, or if he's going towards the left on the screen, that means he's going in the negative direction. And so we simply indicate that by showing it below the x-axis, and that's all it is. So constant negative velocity. Again, our slope here is equal to 0. It's 0, but on the negative side. So again, constant velocity, but in the negative direction. All right. Oops, sorry. Didn't mean to hit that. There we go. All right. How about a velocity time graph of a duck coming to a stop? Okay, what's gonna be happening with this one? So this guy's hitting the water. He's going to be coasting to a stop here. So first thing we got to think about, this is going to be kind of a tricky one. I'll draw it like he's going in the positive direction. Okay, let's pretend like he's going in the positive direction first of all. So let's say that this is our positive direction. So he's going this way. I'm going to define that as being positive in this case. What's his speed doing? Well, his velocity is going from, say, 10 meters per second to 5 meters per second. And if he's coming to a stop, at the end, he's going to be going 0 meters per second. So what is that going to look like? Well, he's going to start at, say, 10 meters per second. Hits the water. He's going to be slowing down over time and eventually coming to 0. When you hit this line, that means your velocity is 0. You're coming to a stop. If I can draw that correctly, ta-da, it would look like that. So we've got positive velocities, but they are decreasing in magnitude. So our slope here is negative. And what does that mean? He's accelerating, but it also means that he's slowing down. Now, negative doesn't always mean slowing down, but in this particular case, he's going from 10 to 7 to 3 to 2 to 1 to 0. He's slowing down is what that particular duck is doing. What happens if he's going the other way? I think this one's starting from rest, right? What happens if he's going the other way? I'm going to do a quick erase, and we're going to do a little redraw on this one. What if we define this the same way that we did before, where this duck is going west, so therefore he should be going the negative direction? Okay, the graph looks real similar. So what would that mean? If he's going the negative direction, let's say this is now negative because he's going west. Well, he's still starting at negative 10 meters per second when he starts, right? That's his fastest speed. And at the end, he's still going to be going 0 meters per second by the time he's done. So it's kind of a mirror image of the graph that we just did. He's starting with a high rate of speed. A high rate of speed here means far away from the x-axis. And he's slowly but surely approaching 0. So again, it would be something like this, like that. And that would mean he's starting with a negative velocity, negative 10 meters per second. He's going west as opposed to east, if I call west the negative direction. He's going 10, 7, 5, 2, and then here he's going 0 meters per second. He has stopped when he's at that 0 line. That's what that means. So now what does this mean? Negative velocities, and here it has a positive slope. This means he is slowing down. So note, it's the signs if they're different, it means he's slowing down. So again, he's starting at negative 10 and approaching 0, he's slowing down. All right, moving forward, a little bit easier. Starting from rest. Okay, if we got our dog friend here starting from rest, he is heading east. East is in the positive direction. So he's starting at 0 meters per second, and then ending at something positive, 10 meters per second. Now what's he going to be doing? Well, he's starting here, 0, 1 meter per second, 2 meters per second, 10 meters per second, whatever it is. Again, in this particular case, we have an upwards slope to it. We've got positive velocities going in the east direction, and he's going increasing in speed, this is speeding up. So again, notice that these signs are now the same. When these signs are the same, speeding up. When these signs are different, slowing down. By the way, if he was going the opposite direction, right? If we were saying that this was the negative direction, it'd be the same thing, just the mirror image of it. It'd be going that way. If he was going west instead of east, he'd be going down that direction, going from 0 to -1 to -2 to -5 to -10 meters per second, whatever it would end up being. Again, if he's going in that negative direction, your line just goes the other way. It's the other quadrant, I guess, of the graph. Okay, what if it's changing its acceleration? Something like this, where we've got something like a race car, which doesn't just go just kind of slowly but surely, but they kind of start slow and they go, right? They speed up, they hit the gas. They don't quite have always the same level of acceleration, changing rates of acceleration. This is the same thing is true like when you guys are coming to a stop. Think about how you stop at a stop sign. You have two ways to stop at a stop sign, right? You can either slam on the brakes and literally screech, come to a stop, and everyone's like, ugh, right? Or you can kind of do the nice come to a stop. They call it feathering the brakes, right? Where you come to a stop and then you kind of like gently like lift off just at the last second. So everyone doesn't like jerk their head forward, right? That's what we're talking about. You've got that change in motion to it. So with this, instead of having a nice straight line, oops, got to get my pen back. Instead of having just a nice straight line where it's changing its velocity in a constant way, if it's changing its rate, starting off slow and then hitting the hammer, it may look more like this, right? Where your velocity is kind of slow, and then as you pick up speed, you really get faster. Or you could do something similar where you hit the gas, literally pedal down. You could be doing something along these lines where it starts off like super steep, right? And then kind of levels out like this. This means you're getting fast, super quick, massive acceleration, and then you're still accelerating, but you're not as accelerating as quickly. Nice hair, Beto. So you can have these different changes in there. So all I wanted to do is point out to you that on a VT graph, velocity time graph, if you see a straight line, like that one is supposed to be, straight line, again, in the perfect world, straight line means constant acceleration. It's increasing by 5 meters per second every second. If you start to see curves in a variety of different shapes, spiking up, leveling off, whatever it is, curves indicate changing rates of acceleration as opposed to constant acceleration. Again, most of the time in physics, we're going to be dealing with constant acceleration or even constant velocities, but constant rates of acceleration, so we don't have the nasty calculus that goes along with changing acceleration. So this brings us up to our last comment in this particular thing, the difference between average acceleration and instantaneous acceleration. So average acceleration is over a time interval. So if we have changing acceleration, we have a couple of different ways that we can deal with it in a physics at this level without calculus. Number one is we typically deal with average acceleration. Okay, I started at this speed, I ended at this speed. What was the overall change? And that is delta V over delta T. This is average acceleration regardless of how it got there. Okay, it could have gone this way, it could have gone this way, it could have gone any of these different paths. If it started at 0 and it ended at 100 and it took 6 seconds to get there, the average acceleration is the same. So that's one of the major things that we do, is that we sort of make it linear. We deal with it via average because the average acceleration is always start to finish over time. It's always a straight line hypotenuse. The other way that we can talk about it a little bit is through this concept of instantaneous acceleration. Instantaneous acceleration, this one right here talks about slope, right? Slope of the line, the overall start to finish, what's our delta V and what's our delta T? By the way, this over here, from here to here, that's delta T, right? And from here to here, like here to here, that's delta V, right? We've got that distance over time. As opposed to instantaneous acceleration is what is happening at each of these points. And we're going to do this. Hold on, let me finish writing it. If we want to talk about how its acceleration is changing over time, then we need to talk about the slope of the tangent line. Now, we're not going to do this in anything more than a philosophical way. I'm not going to make you calculate this. I just want you to be able to recognize sort of what that tangent line slope is, and to hopefully recognize that that's actually what calculus does. Calculus takes the slopes of all of these different tangent lines and sort of averages them together. So if you take a look at what a tangent line is, remember a tangent line touches a curve at one and only one point. In a sense, it's perpendicular to the curve. It's kind of one way to think about it, I guess. So if we take a look at our slopes here, our slope would kind of look like this for that line, kind of look like this for this line, this for this line, and it kind of gets steeper each time. As opposed to this one, it starts off like that. It starts off like that. This one's, I'm doing a little better on this one. Flatter, flatter, and then flatter yet. And this one maybe is leveling off this way versus this one down here is actually getting as steep as possible. So the changing slopes of those tangent lines gives you a better idea of the instantaneous acceleration of what's happening. If it's starting off relatively flat, that means its earlier accelerations are relatively less, and then the acceleration is getting greater, greater, greater every time we go. This, at the end of this bottom curve, that last slope is relatively steep, showing its greatest rate of acceleration, biggest jerk. As opposed to this one, the acceleration is kind of leveling off, right? It had the blast off kind of thing where it's accelerating a whole bunch right at the first and then is approaching a constant velocity. It's not accelerating as much. So you can see from these instantaneous accelerations, some of those rates have changed. So again, all I want you to kind of get the idea is average acceleration is what we are typically doing. We just talk about the linear acceleration over time, averaging it out. Again, without calculus, that's as much as we can really do. With calculus, you can start to take these instantaneous accelerations, these individual spots, and start seeing how the rate of those changing slopes starts to average out over time. And that's what we'd actually do, like I said, in a calculus-based class. So just as a brief introduction to what we've got with velocity time graphs, most of the time we will be dealing with linear velocity time graphs, but now you know kind of how you can sort of deal with or interpret curving velocity time graphs and looking at their individual instantaneous accelerations. So there you go. Mostly what we're doing, again, linear velocity time graphs. See you in the next one, guys. Bye.